Hello, grade 10s. In today's lesson, we're going to start on chemical bonding, which is part of the topic of matter and material. And this is, in fact, the last section of matter and material. In this section, we are going to define a chemical bond, a covalent bond, and an ionic bond. Those are specific types of chemical bonds. We are going to learn how to draw Lewis dot diagrams of elements, how to draw Lewis dot diagrams of covalent molecules, and Lewis dot diagrams of ionic compounds, also showing half reactions, full reactions, and the final product. We're going to learn common cations and anions, the ones that we cannot identify on the periodic table. Remember that group 1, 2, and 13 to 17, we can work out what cations and anions those elements make based on their group number. We're also going to define a metallic bond, and we're going to learn how to calculate the relative atomic mass and the relative formula mass for covalent molecules and for ionic compounds, respectively. So let's start off by understanding and defining chemical bonds. Now, when a chemical bond forms, it's a physical process that causes atoms to be attracted to each other, and it causes them to be held together. And what holds atoms together in a chemical bond is the electrostatic force of attraction between the nucleus, where the protons live, which are positively charged, and the electron clouds, which is where the electrons live, and those are negatively charged. So in a chemical bond, we have an electrostatic force of attraction that holds atoms together due to the forces of attraction between their nuclei and their electron clouds. So let's define a chemical bond. It is a strong electrostatic force of attraction that holds atoms or ions together, resulting from the simultaneous attraction between their nuclei and electrons. Just remember that in the nucleus is where the positively charged protons live. Now, depending on the atoms involved, there will either be a covalent bond or an ionic bond or a metallic bond. A covalent bond specifically exists between nonmetals. Note that a metalloid and a nonmetal, when they bond, it is also a type of covalent bond. And very important is that in a covalent bond, atoms share their electrons. The sharing of electrons is what results in an electrostatic force of attraction, because it is those shared electrons that attract the nuclei of both atoms, or sometimes it's more than two atoms, but of the atoms that are involved in the covalent bond. When we draw Lewis dot diagrams for covalent bonds, you will see how those electrons are shared. Then we'll learn about ionic bonds. Now, ionic bonds typically exist between a metal and a nonmetal, sometimes more than one nonmetal, but there's always a metal involved. And in the case of an ionic bond, electrons are transferred from the metal to the nonmetal. So the metal becomes positively charged because it gives away electrons, while the nonmetal becomes negatively charged because it gains electrons. And now that one atom is positively charged and the other atom is negatively charged, there exists an electrostatic force of attraction between the atoms, which is what holds them together. That is the ionic bond that holds them together. In a metallic bond, well, that exists either in one metal, so say you have a piece of iron, then that means that there is a metallic bond between all those atoms of iron, or a mixture of different types of metals. Either way, what happens is that the valence electrons of the metal atoms become delocalized. They lose track of who they belong to. That doesn't apply to the core electrons. It is only the valence electrons that experience this. And so that results in a positively charged metal ion because it has lost its valence electrons. And all those valence electrons are now swimming around and they create an electrostatic force of attraction between themselves and the positive metal ion. But we'll look at diagrams of that to clarify a little bit later. Let's start off by learning how to draw electron dot diagrams using Lewis notation. We learned that atoms have core electrons and then they also have valence electrons. And it is the valence electrons that determine the properties of the element because it is those valence electrons that are involved in chemical bonds. Now, based on the arrangement of the elements on the periodic table, we can figure out the number of valence electrons based on the group number. So we know that group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Group 13 elements have 3 valence electrons because remember we skipped the D block. Group 14 elements have 4 valence electrons. Group 15 elements have 5 valence electrons. Group 16 elements have 6 valence electrons. Group 17 elements have 7 valence electrons. And our group 18 elements are the noble gases. They have a full outer energy level with 8 valence electrons, while helium has 2 valence electrons. Lewis notation is a system of dots and crosses to help us to represent the number of valence electrons of an atom. We start off by writing the element of the atom that we're interested in, and then we draw dots around the symbol of the element. Now, we don't pair them up. So the first 4 dots are drawn as one on each side. We usually start at the top and we move in a clockwise direction. That is not a must. You can actually start anywhere and then move either in a clockwise or an anti-clockwise direction. So as long as you keep that organization, then that's fine. But I always tell my students to start at the top and move clockwise. Now, if there are more than 4 valence electrons, then they start to pair up. Let's see what I mean by that. So for example, hydrogen is in group 1. It has 1 valence electron. So the Lewis dot diagram of hydrogen is simply the symbol of hydrogen, H, with 1 valence electron. Magnesium is in group 2, so it has 2 valence electrons. So here's the electron dot diagram or the Lewis dot diagram. I've got 1, 2. So I start at the top and I go clockwise. Now, one exception is helium. It has 2 valence electrons, but in the case of helium, helium has a full outer energy level. So both of its valence electrons are actually technically also core electrons. So in the case of helium, we want to keep these 2 dots together. We don't separate them out like we do in the case of magnesium. And again, that is an exception because helium is a noble gas. Now, oxygen is in group 16, so it has 6 valence electrons. So we go 1, 2, 3, 4, and after the 4th one, we start to pair those valence electrons, 5 and 6. Argon is in group 18. It has 8 valence electrons. So the Lewis dot diagram of argon will show us all 8 electrons around the argon atom. Most elements combine to form molecules so that they have 8 valence electrons. That is very important when we draw Lewis dot diagrams. We need to make sure that our molecules have 8 valence electrons around them. And that is because 8 valence electrons means a full outer energy level. Having the full 8 electrons in the outermost energy level makes the element stable. One exception is hydrogen. Because remember, for hydrogen to have a full outer energy level, it needs two valence electrons. So when we draw Lewis dot diagrams, we need to remember that hydrogen needs to have two valence electrons around it, whereas every other element needs 8 valence electrons to surround it. So let's now look at covalent bonding. What is a covalent bond? A covalent bond is defined as the sharing of electrons between nonmetals. And here's a visual that shows a sharing of electrons. One electron belongs to one atom and another electron belongs to another atom. So in a covalent bond, the atoms share their electrons. Let's look at the covalent bond that exists in hydrogen chloride. Hydrogen has one valence electron. We know that because hydrogen is in group 1. The first energy level can only fit 2 electrons. So remember that hydrogen only needs one more electron to have a full outer energy level. All other elements need 8 valence electrons. Chlorine has 7 valence electrons around it, and we know that because it is in group 17. So chlorine needs one more electron to have a full outer energy level. And we can use Lewis dot diagrams to help us represent how that bond is formed. So we've got hydrogen, which has got one valence electron, and we've got chlorine, which has got 7, and we can clearly see that with hydrogen sharing an electron and chlorine sharing an electron, hydrogen now has a full outer energy level because it's got 2 electrons around it, and chlorine also has a full outer energy level because it has 8 electrons around it. So here we can see the covalent bond that forms in the case of hydrogen chloride, which is also known as hydrochloric acid. As we can see, hydrogen is sharing one electron and chlorine is sharing one electron, and that makes what we call a single bond. So we can also represent a single bond. This line over here is a representation of a single bond, and it indicates to us that one of the electrons in that bond belongs to hydrogen and one of the electrons in that bond belongs to chlorine. So the single line represents that each atom shares one of its electrons. Note that the total number of valence electrons does not change. The electrons are shared in such a way that both hydrogen and chlorine have a full outer energy level. Let's look at the covalent bond in carbon tetrahydride, CH4. CH4 has the common name of methane. Hydrogen has one valence electron. So each hydrogen atom here needs one more electron in order to have a full outer energy level. Carbon has 4 valence electrons, so it needs 4 more electrons to have a full outer energy level. So that gives us a good indication of what that bond is going to look like. We've got carbon with 4 valence electrons. We've got hydrogen, 4 of them, each one with 1 valence electron. Now, with each hydrogen atom sharing one of its electrons with carbon, we get the formation of this covalent bond. Now, take a look at each hydrogen atom has 2 valence electrons around it, and that makes its outer energy level full, so it's happy. And carbon now has 8 valence electrons around it, so carbon is also happy. Now we can understand why a carbon atom bonds with 4 hydrogen atoms. In this case, there are 4 single bonds surrounding the carbon atom. And a single bond is made up of one shared pair of electrons, meaning one electron comes from carbon and the other electron comes from hydrogen. And this may be represented like this, with single lines, where each line represents a shared electron pair. Now, two things that I didn't mention previously. You would have noticed that for HCl and for CH4, I use dots and crosses. Now, it's called a Lewis dot diagram. You don't have to use dots and crosses. You can just use dots, but crosses are sometimes nice to use because it helps you track which electron belongs to which atom. The other thing that we need to keep in mind is that if we're going to represent our Lewis dot diagrams and our bonds as single lines for a single bond, then we also need to make sure that we need to include any other electrons that are not shared around the atoms. So in this case, there are no electrons that are not bonded around the hydrogen, but in the previous case with HCl, chlorine still had its own electrons, its own valence electrons that are not shared in the bond surrounding it. So we also need to include that around the chlorine atom. We can't leave that out. Let's consider the covalent bond in CO2. Carbon has 4 valence electrons, so it needs 4 more electrons to have a full outer energy level, whereas oxygen has 6 valence electrons, so it needs 2 more electrons to have a full outer energy level. Now, the fact that we've got 2 oxygen atoms, and each oxygen atom has 6 valence electrons, and it needs 8 valence electrons, that already should raise some awareness in us that oxygen and carbon will each bond with a double bond. Let me explain. How do we know, first of all, which atom goes in the center? Now, when hydrogen is involved, which it is not in this case, hydrogen always goes on the ends. But aside from hydrogen, the central atom is the one that has the lowest electronegativity. Now, what is electronegativity? This is a definition that you do need to know in grade 10, but we don't really work with electronegativity very much in grade 10. It's more part of your grade 11 syllabus. But here's the definition. It's the tendency of an atom in a molecule to attract bonding electrons closer to itself. So electronegativity is really how much does a particular atom within a molecule attract electrons towards its side. Now, we're going to learn more about it in grade 11, but on your periodic table, you'll find that electronegativity is the number to the left of the element. So remember, the central atom is the one with the lower electronegativity, and electronegativity is represented as the number on the left of the element. So carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. Now, hydrogen, we said, always goes on the ends, even though it has quite a low electronegativity, so don't forget that as an exception. And back to our carbon dioxide example, which one will be the central atom, carbon or oxygen? Well, carbon has a lower electronegativity, so carbon will be the central atom. Now, it gets quite tricky, especially when hydrogen is not involved. We need to think of a way to arrange the electrons around the atoms in such a way that each atom has 8 valence electrons around it, meaning that it has a full outer energy level. And so far, we've only looked at a single bond, but there is also the existence of a double bond and a triple bond. A single bond means that there is one shared pair of electrons, whereas in a double bond, there are 2 shared pairs, and in a triple bond, there are 3 shared pairs of electrons. Now, because oxygen needs 2 more electrons, and we know that oxygen goes on the ends, that immediately suggests to us that a double bond is involved. If an oxygen atom shares 2 of its electrons with 2 of carbon's electrons, then it will have 8 electrons around it. We're going to draw a Lewis dot diagram to help us represent this. So here we have the Lewis dot diagram of a carbon atom, and here we have the Lewis dot diagram of an oxygen atom. But because it is CO2, we know that we have 2 oxygen atoms involved. We also know that the oxygens go on the ends and carbon is the central atom. So the circles or dots represent carbon's 4 valence electrons, and the crosses represent the 6 valence electrons of oxygen. And by creating a double bond, because here we've got one shared pair, another shared pair, that's a double bond. Here we have one shared pair and another shared pair, that's another double bond. We can now see that carbon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons around it. And each oxygen atom also has 8 valence electrons around it, 6 of its own plus the 2 of carbon. I want you to note that once we have created bonds, the electrons do not exist on their own. We should never ever separate this electron and put it at the bottom. They've got to stay in pairs. The other thing we need to note is that the one pair is going to move as far away as possible from this bonded pair due to forces of repulsion of electrons. So one pair goes here, and then the second pair goes either at the top or at the bottom. That means you shouldn't place a pair at the top and a pair at the bottom. One pair should move as far away as possible from the bonded pair. Same applies to this side over here. Now this may also be represented with a double bond on either side of carbon, because there are 2 pairs of electrons that are shared by each atom. So these bonds may be represented by lines. Each line represents a shared pair of electrons. And also note that the rest of the valence electrons that are not involved in the bonding surrounding the oxygen atom still need to be shown, and they need to be paired. Like I said previously, you should never separate them. And like I said previously, one pair should be placed as far away as possible from the bonded pair due to the strong forces of repulsion between negatively charged electrons. Let's consider the covalent bond in HCN. Now remember that hydrogen, regardless of its electronegativity, always goes at the end of a molecule. Then if you refer to your periodic table, you'll see that carbon has an electronegativity of 2.5 and nitrogen has an electronegativity of 3. So which one is the central atom? Again, it will be carbon. So that helps us to set up our molecule. Now, hydrogen has 1 valence electron. So it needs 1 more electron, which it's going to have to get from carbon, because the hydrogen is going to be next to the carbon on one end. Carbon has 4 valence electrons. It needs 4 more electrons to have a full outer energy level. And nitrogen has 5 valence electrons, so it needs 3 more electrons. Now we know that the nitrogen is going to be attached to the carbon, so those 3 valence electrons are going to have to come from the carbon. That immediately indicates to us a single bond on one end and a triple bond on the other end. So we need to think of a way to arrange the electrons around the atom so that each atom has 8 electrons around it, so that it has a full outer energy level, except for hydrogen, which needs 2. And remember that we can use single or double or triple bonds. So again, because hydrogen only needs 1 more electron, this suggests a single bond. Because nitrogen needs 3 more electrons, This suggests a triple bond. We use a Lewis dot diagram to help us represent the bonds. So we've got hydrogen with 1 valence electron, carbon with 4 valence electrons, and nitrogen with 5 valence electrons, forming HCN. Now we can see that hydrogen's got 2 valence electrons around it, so it is happy. Nitrogen has got 8. 2 plus 3 plus 3 makes 8, so nitrogen's happy. And carbon is also happy because it has 8 valence electrons around it. 3 plus 3 plus 2 again makes 8. Now, this may also be represented with a single bond between carbon and hydrogen and a triple bond between carbon and nitrogen, like this. Remember that the other valence electrons that are not involved in bonding, which in this case will only belong to the nitrogen, need to be shown, and they need to be paired, and they need to be as far away as possible from the bonded pairs of electrons. Another important note is that a triple bond is stronger than a double bond, which is stronger than a single bond. What I'd like you to do next is to practice drawing Lewis dot diagrams for covalently bonded molecules. It is tricky and it requires practice. There are no shortcuts here. I would like you to firstly represent each bond using dots and crosses, and then again using lines for single, double, and triple bonds. Try the exercise on your own before you look at the answers. Let's take a look, starting with hydrogen. Hydrogen gas is H2, it's a diatomic molecule. Each hydrogen atom has 1 valence electron, so by sharing their valence electrons, they create a single bond. CH4, we already covered together. Carbon has 4 valence electrons, and each hydrogen atom surrounding the carbon atom contributes 1 valence electron. Therefore, there are 4 single bonds around the carbon atom. NH3. Well, why does nitrogen bond to 3 hydrogen atoms in the creation of ammonia? That's because nitrogen has 5 valence electrons of its own, and then each hydrogen atom contributes a valence electron. So we have 3 single bonds surrounding the nitrogen atom, where hydrogen is bonded to the nitrogen. And don't forget, you can't leave out this lone pair of electrons that belongs to nitrogen that is not actually part of the bond. Next is HCl, which we also covered together. Chlorine has 7 valence electrons, hydrogen has 1, so there is a single bond formation between hydrogen and chlorine. And don't forget to show the rest of chlorine's electrons that are not involved in the bond. H2O. Well, oxygen has 6 valence electrons, and each hydrogen atom has 1 valence electron. So that gives us a clue that there would be 2 single bonds on either side of the oxygen atom. So here we can see with the crosses, we've got 1, 2, 3, 4, 5, 6. Those are the valence electrons that belong to oxygen. And then each hydrogen atom contributes a valence electron. So there is a single bond on either side of the oxygen atom, bonding oxygen to hydrogen. And then we still need to show the electrons of oxygen that are not involved in bonding. Nitrogen. Nitrogen is a diatomic molecule. Each nitrogen atom has 5 valence electrons. How many more electrons does each nitrogen atom need? 3 because 5 plus 3 makes 8. And that immediately tells us that there is going to be a triple bond. By arranging nitrogen in such a way that there is a triple bond that bonds the two nitrogen atoms, each nitrogen atom now has 8 valence electrons around it. We can also show it like this, as a triple bond, and remember that the electrons that are not involved in bonding are going to be placed as far away from the bonded electrons as possible. Oxygen is also a diatomic molecule. Each oxygen atom has 6 valence electrons, and so as a result, it needs another 2, which indicates to us that there is going to be a double bond involved. So here we can see that with the aid of a double bond, each oxygen atom has 8 valence electrons around it. And note that one of the pairs of each oxygen that's not involved in bonding moves to the end, and then the other pair can either go to the top or to the bottom. Fluorine, again, a diatomic molecule. Fluorine, chlorine, iodine, bromine, those are all diatomic molecules that are in group 17, meaning that they have 7 valence electrons, meaning that they only need one more electron in order to have a full outer energy level, and that indicates to us a single bond. So here we can see nicely and clearly, because we've got colors and dots and crosses, the 7 electrons of fluorine and the other 7 valence electrons of the other fluorine atom, and with the aid of a single bond, they can each have 8 valence electrons around them. So chlorine will bond in exactly the same way. So would iodine, I2. So would bromine, Br2. Let's take a look at H2S. Sulfur has 6 valence electrons, and each hydrogen has 1 valence electron. This is going to be a similar setup to H2O. So here we can see that there is a single bond that bonds the sulfur and the hydrogen on either side, and sulfur still has 1 pair at the top and 1 pair at the bottom of electrons that are not shared. But now the sulfur atom has 8 valence electrons around it, and each hydrogen atom has 2. Hydrogen fluoride, HF, or fluorine, has 7 valence electrons and hydrogen has 1 valence electron. This is a similar scenario to HCl, where there is a single bond that bonds the hydrogen and the fluorine, and fluorine still has its 6 non-shared electrons surrounding it. Let's take a look at silicon dioxide. Silicon is a semi-metal. And remember that semi-metals bond covalently to nonmetals. So we're going to use the Lewis dot structure of covalent bonds for silicon dioxide. Silicon is in group 14. Therefore, it has 4 valence electrons. Each oxygen atom has 6 valence electrons. Silicon has a lower electronegativity than oxygen. Therefore, it will be the central atom. So here we can see that silicon has got 2 and another 2 electrons that belong to it. It's a similar scenario to carbon dioxide, which also has 4 valence electrons. By creating a double bond on either side with each oxygen atom, silicon now has 8 valence electrons around it. And we can see that with the aid of a double bond, each oxygen atom has 8 valence electrons around it. And finally, CH2O. Remember that hydrogen always goes on the ends. So which is going to be the central atom? The one with the lower electronegativity, which is carbon. So carbon will be in the middle, and the two hydrogen atoms and the oxygen atom will surround the carbon atom. Now, hydrogen only needs one more valence electron to have a full outer energy level, so there has to be a single bond with hydrogen. There can only ever be a single bond with hydrogen. Now, by creating a double bond with oxygen, carbon can have 8 valence electrons around it. The oxygen can now have 8 valence electrons around it, and each hydrogen atom has 2 valence electrons around it. And don't forget that oxygen's electrons that are not shared still need to be shown around oxygen. One pair has to be placed as far away as possible from the bonded pair, which is here up top, and then the other pair can either be placed on the left or on the right-hand side of the atom.